Settle into the sleepy mind channel. Tonight, we will explore how gemstones form underground, far below mountains, deserts, forests, and oceans, in places shaped by heat, pressure, molten rock, and long periods. Some gemstones began forming more than 3 billion years ago, long before humans built cities, crossed oceans, or even understood what lay beneath the ground beneath their feet. Deep inside Earth, hidden from sunlight and weather, minerals slowly gathered into crystals through quiet geology, unfolding over thousands, millions, and sometimes even billions of years. What later becomes a polished ruby, sapphire, emerald, or diamond often begins in darkness under conditions so extreme they are difficult to imagine. Temperatures rise high enough to soften rock itself. Pressure grows immense beneath miles of stone. Atoms slowly arrange themselves into repeating patterns more orderly than many structures humans have ever built. If you enjoy relaxing educational sleep stories like these, feel free to like and subscribe and explore the playlists filled with calm topics designed for long night listening and gentle learning. Gemstones are not formed quickly or carelessly. Their formation depends upon precise conditions underground where temperature, pressure, chemistry, and time combine in specific ways. Even slight differences in these conditions can change the type of crystal that forms. Some minerals remain ordinary rock. Others slowly become transparent crystals, capable of bending and reflecting light in beautiful ways. Gemstones spend most of their existence hidden long before humans ever discover them. A crystal may form beneath an ancient mountain range and remain buried there for millions of years before erosion, volcanic activity, or shifting rock finally brings it closer to the surface. The Earth itself is layered almost like a giant stone sphere, built from different regions stacked one beneath another. Humans live on the outer crust, which is extremely thin compared to the total size of the planet. Beneath that crust lies the mantle, a vast region of intensely hot rock extending deep into the Earth. Farther still lies the core, where temperatures become extraordinarily high. As depth increases underground, conditions become more extreme. Heat rises steadily. Pressure increases enormously from the weight of rock above. These hidden conditions shape the minerals forming inside Earth and influence how crystals develop over time. Pressure underground is difficult to imagine because humans rarely experience anything remotely similar in ordinary life. Even standing at the bottom of the ocean would expose a person to only a tiny fraction of the pressure existing underground. Miles of rock press downward from a direction. Minerals are squeezed tightly together, while heat increases molecular activity inside the rock itself. Under these conditions, ordinary materials can transform into entirely different crystal forms. Carbon, for example, may become diamond when exposed to the correct combination of depth, heat, and pressure underground. Heat also plays a central role in gemstone formation because rising temperatures influence how atoms move and bond together. Underground, rock may soften, partially melt, or interact with mineral-rich fluids moving through fractures and cavities. Some gemstones begin forming from magma, which is molten rock underground. Others form when existing rocks are altered under intense heat and pressure. In a case, temperature helps guide the arrangement of atoms as crystals slowly grow underground over time. Humans often think of gemstones as objects of beauty or jewelry, yet from a geological perspective, they are physical records of ancient Earth processes. A crystal contains clues about the conditions under which it formed. Its structure reflects pressure and temperature. Its color may reveal tiny traces of chemical elements locked inside the crystal during growth. Some gemstones preserve evidence of volcanic activity, deep mantle conditions, or mineral-rich water moving through underground rock long ago. In this way, gemstones are almost like natural archives, recording hidden events from underground. Another reason gemstones fascinate people across cultures and history is because they seem strangely timeless. Ancient civilizations valued crystals thousands of years ago, often associating them with power, protection, beauty, or mystery. Yet the stones themselves were already ancient, long before those civilizations existed. A gemstone held in the hand today may have begun forming before mammals walked the earth or before continents reached their modern shapes. The deep timescales involved in geological formation often make human history feel brief by comparison. The formation of crystals also reveals something about nature itself. At the atomic level, minerals are not random collections of material. Atoms arrange themselves into repeating organized patterns by the laws of chemistry and physics. These repeating structures influence the shape, hardness, color, and behavior of the final crystal. Under the right conditions, nature builds astonishing geometric forms underground without guidance or intention. Sharp crystal points, smooth faces, and symmetrical structures emerge gradually as atoms continue aligning over time. Growth underground is usually extremely slow. Unlike ice forming quickly in a freezer or salt crystals appearing after water evaporates, many gemstones develop over time while conditions remain stable underground. Some crystals may grow only tiny amounts over thousands of years. Others form in underground cavities, where minerals slowly collect layer by layer from heated fluids moving through rock. Time itself becomes one of the most important ingredients in gemstone formation, because ordered crystal growth depends upon long, uninterrupted geological stability. The hidden environment where gemstones form is far more active than many people imagine. Underground, the earth is always changing. Rock shifts slowly through tectonic movement. Magma rises through fractures beneath volcanoes. Heat flows upward from deeper regions. Water carrying dissolved minerals moves through cracks inside the crust. Pressure changes as mountains rise and erosion removes surface layers over millions of years. Beneath the still appearance of the landscape above, geological processes continue shaping minerals and crystals continuously. Tonight, beneath mountains, deserts, forests, and oceans, deep within layers of heated rock hidden underground, crystals continue forming slowly in darkness beneath immense pressure and ancient forces. Long before they become gemstones resting in sunlight or human hands, they begin as quiet mineral structures growing inside the restless interior of Earth. Far underground, deeper than the roots of mountains and far below underground rivers or caves, conditions begin changing in powerful ways. The farther downward a person could travel underground, the hotter the environment would become. Pressure would also rise steadily from the enormous weight of rock stacked above. These two forces, heat and pressure, shape much of the hidden geology inside Earth and play a central role in the formation of gemstones. Although the ground beneath our feet may appear solid and still, the deeper regions of the Earth are active places filled with movement, energy, and transformation occurring over time. Temperature increases with depth, because heat from the interior of the Earth slowly moves outward toward the surface. Some of this heat remains from the planet's violent formation billions of years ago, when enormous collisions and gravitational forces generated tremendous energy. Additional heat is produced through radioactive processes occurring naturally inside certain minerals underground. Together, these sources create a gradual increase in temperature as depth increases underground. Near the surface, temperatures remain relatively moderate compared to the deeper mantle below. Yet only a few miles downward, conditions become dramatically hotter. In some deep environments, temperatures rise high enough to soften or partially melt rock itself. This underground heat influences how minerals behave, how atoms bond together, and how crystals slowly develop over time. Without these elevated temperatures, many gemstones would never form at all. Pressure also increases steadily with depth because of the immense mass of rock pressing downward from above. Even a single cubic mile of stone weighs an astonishing amount. Underground, layers of rock accumulate over one another across enormous distances, creating crushing pressure in a direction. Minerals trapped within these environments are compressed tightly, while heat continues affecting their internal chemical activity. Humans rarely experience pressure on this scale in ordinary life. The strongest industrial machines ever built produce only tiny fractions of the pressure found naturally within some deep regions of the Earth. Even ocean pressure, which feels immense to human divers and submarines, is far smaller than the forces existing deep within the mantle. Yet certain gemstones require precisely these extreme conditions in order to form correctly. Heat and pressure together influence mineral formation by changing how atoms behave inside rock. Atoms are constantly moving and interacting, even within solid materials. Under increasing temperature and pressure, these interactions become more dynamic. Existing minerals may transform into new forms. Chemical elements may combine differently. Crystals may slowly begin developing ordered internal structures capable of growing over long geological periods. Crystals are not random arrangements of material. Instead, atoms organize themselves into repeating patterns by physical and chemical laws. These repeating arrangements form the internal structure of a crystal. Although the process happens invisibly at the atomic level, it creates the larger shapes and physical properties people recognize in gemstones. The structure of a crystal determines many of its characteristics. Hardness, shape, transparency, and even the way light travels through the stone all depend partly upon atomic arrangement inside the crystal. Two minerals containing similar elements may behave differently if their atoms are arranged in different patterns. This is one reason conditions matter so much. Heat, pressure, chemistry, and time all influence how atoms organize themselves underground. Humans often compare crystal formation to building patterns from tiny blocks or arranging tiles across a floor in repeating designs. If each piece is placed carefully by a consistent pattern, larger organized shapes gradually emerge. Nature accomplishes something somewhat similar with atoms underground. Under stable conditions, atoms align into repeating structures over time, slowly creating crystals with order and symmetry. The deeper regions of the Earth provide environments where these patterns can develop slowly without constant disturbance. In some underground settings, crystals may continue growing for thousands or even millions of years while surrounding conditions remain relatively stable. Heat keeps atoms active enough to bond and rearrange, while pressure compresses materials together in ways influencing crystal structure and mineral transformation. Some gemstones form only within narrow ranges of temperature and pressure. If conditions become too hot, crystals may melt or break down. If pressure becomes too low, certain crystal forms may never develop correctly. Geological environments therefore act almost like natural laboratories, where only specific combinations of conditions allow particular gemstones to form. This is one reason many gemstones remain relatively rare compared to ordinary rock minerals found near the surface. The Earth itself is always changing over time, which means underground conditions also shift slowly. Tectonic plates move, mountains rise, continents drift, magma travels upward through fractures beneath volcanoes. Rock layers sink deeper or rise closer to the surface over millions of years. During these long geological cycles, minerals experience changing environments that may support crystal growth or transformation. Even though gemstones often appear calm and still when polished and displayed, their origins are connected to some of the most powerful forces operating within the planet. Extreme pressure, deep heat, shifting rock, and ancient geological movement all contribute to their formation. A crystal carries a hidden history shaped by environments humans cannot directly visit because they exist underground. Beneath mountains, valleys, deserts, forests, and oceans, minerals continue responding to rising heat and immense pressure. Atoms slowly align into repeating patterns, while forces shape crystal growth over stretches of time far longer than human history. In darkness underground, the Earth continues building gemstones through heat, pressure, and the quiet order of natural crystal formation. Gemstone begins with chemical elements already present underground. Long before a crystal develops shape, color, or transparency, tiny particles of matter exist underground within rock, magma, fluids, and minerals moving through the planet over time. These elements are the basic ingredients from which minerals form. Some are extremely common, while others appear only in smaller amounts under specific conditions. Together, they create the enormous diversity of minerals and gemstones found across the Earth. An element is a pure chemical substance made from only one type of atom. Gold is an element. Carbon is an element. Oxygen, iron, silicon, and aluminum are also elements. Underground, these atoms constantly interact with one another as heat, pressure, and geological movement influence the environment around them. Under the correct conditions, elements begin combining together into more complex chemical arrangements known as compounds. Many minerals are compounds formed from several elements bonded together in stable patterns. Quartz, for example, forms when silicon and oxygen combine in repeating crystal arrangements. Corundum, the mineral family that includes ruby and sapphire, contains aluminum and oxygen. Emerald contains additional elements including beryllium, aluminum, silicon, and oxygen combined together under specific conditions. The exact mixture of elements inside a mineral strongly influences the crystal that develops. Many environments allow these combinations to occur. Deep within magma chambers, elements move through molten rock heated far beyond the boiling point of water. In metamorphic regions, older minerals are altered by rising pressure and temperature. In underground fractures, mineral-rich water carries dissolved elements through cracks and cavities in the crust. Throughout all these environments, Atoms constantly interact and reorganize themselves by physical and chemical laws. Crystallization begins when conditions allow atoms to settle into organized repeating arrangements. Instead of remaining randomly scattered, atoms bond together in highly ordered patterns that repeat over and over again throughout the growing crystal. This process does not happen instantly. Crystallization unfolds slowly over time, while underground conditions remain stable enough for organized growth to continue. Humans sometimes compare crystallization to snowflakes forming within clouds during winter. Water molecules arrange themselves into repeating geometric forms as ice crystals develop. Although gemstones form under entirely different conditions and over vastly longer timescales, the underlying principle of organized atomic structure remains similar. Nature repeatedly builds order from tiny particles through consistent physical rules operating over time. The arrangement of atoms inside a crystal is extremely important because it determines many of the mineral's properties. Hardness, shape, cleavage, transparency, and light reflection all depend partly upon internal atomic organization. Even when two minerals contain some of the same elements, they may become entirely different substances if the atoms are arranged differently. Structure matters just as much as composition. Carbon provides one of the most famous examples of this principle. Under certain conditions, carbon atoms bond together into diamond, creating one of the hardest known natural materials. Under different conditions, carbon may instead form graphite, the soft material commonly found in pencils. Both substances contain carbon, yet their atomic structures differ completely, producing dramatically different physical properties. The process of crystallization often requires stability over time because atoms need time to organize themselves into repeating patterns. If conditions change too rapidly, crystals may remain small or poorly formed. Slow cooling, gradual mineral deposition, and relatively stable environments often allow larger and more organized crystals to develop. This is one reason some gemstones form as impressive crystal structures, while others remain tiny grains hidden within ordinary rock. Underground, crystallization may occur within molten rock, slowly cooling underground. As temperatures gradually decrease, different minerals begin forming at different stages depending upon their chemistry. Some elements bond together early, while temperatures remain extremely high. Others crystallize later as the environment cools further. Over time, this process creates complex mixtures of minerals within underground rock formations. In other environments, crystals form from heated water, carrying dissolved elements through fractures inside rock. As temperature, pressure, or chemistry changes, dissolved materials may begin crystallizing along the walls of underground cavities. Layer after layer slowly accumulates while crystal faces continue growing outward into open space. Some of the most beautiful crystal formations on Earth develop through these quiet underground processes unfolding over time. The repeating structures inside crystals are so orderly that they often produce recognizable geometric shapes visible to the eye. Sharp points, smooth flat surfaces, and symmetrical forms all reflect the organized arrangement of atoms within the crystal itself. Nature creates these structures automatically through chemistry and physics without intention or design. The same natural laws guiding atoms underground continue operating consistently throughout the Earth. Scientists studying crystals often use specialized tools capable of examining atomic structure directly. because the internal arrangement reveals valuable information about how the mineral formed. Crystal structure may record pressure conditions, temperature ranges, cooling rates, or chemical environments existing underground long ago. In this way, gemstones preserve hidden evidence about the ancient conditions under which they developed. The timescales involved in crystallization are often difficult for humans to fully imagine. Some crystals may continue growing over periods far longer than recorded human history. While civilizations rise and disappear at the surface, minerals underground continue organizing atom by atom beneath mountains, deserts, forests, and oceans. Geological time moves slowly compared to human life, yet crystal growth continues underground. Tonight, underground where heat, pressure, chemistry, and time combine in darkness beneath layers of stone, atoms continue aligning into repeating structures. Elements bond together into compounds, while crystals slowly form through quiet geology unfolding underground. Gemstones continue growing one atom at a time within the hidden interior of Earth. Underground, crystals grow by patterns so organized that they almost appear designed, yet a shape emerges naturally from the arrangement of atoms inside the mineral itself. Long before a gemstone becomes polished or cut by human hands, its structure is already being shaped at the microscopic level through repeating geometric order. These repeating atomic patterns guide how crystals expand, how their surfaces develop, and even how light later moves through them. The beauty visible in gemstones often begins with invisible organization unfolding underground over time. When atoms bond together inside a crystal, they do not arrange themselves randomly. Instead, they follow stable repeating patterns determined by chemistry and physical laws. Each mineral develops its own internal arrangement depending upon the elements involved and the conditions under which the crystal forms. These repeating patterns extend throughout the growing mineral, almost like a carefully organized framework hidden. Humans often notice the outward shapes of crystals without realizing those shapes reflect internal structure. Sharp points, flat surfaces, six-sided forms, cubes, and long columns all emerge because atoms are repeating in highly organized ways inside the crystal itself. The outer appearance is essentially a visible expression of invisible atomic order hidden deep within the mineral. Quartz crystals provide a familiar example of this relationship between structure and shape. Many quartz crystals develop long six-sided forms ending in pointed tips because the internal arrangement of silicon and oxygen atoms encourages growth along specific directions. Other minerals form cubes, thin sheets, or branching structures depending upon how atoms bond together inside the crystal. The geometry visible outside reflects the geometry repeating inside. This process resembles architecture in certain ways. A building's outer form depends heavily upon its internal framework and support system. The hidden arrangement inside determines how the structure expands upward and outward. Crystals behave somewhat similarly because internal atomic order guides the external form that develops during growth underground. Growth conditions also strongly influence crystal appearance. Even when two crystals contain the same elements, differences in temperature, pressure, space, and chemical environment may change how they develop. One crystal may remain small and compact, while another grows into large transparent forms with sharply defined surfaces. Environment shapes the final result just as much as chemical composition. Space is especially important for crystal development because crystals require room to expand outward while growing. In crowded environments where minerals compete for limited space, crystals may become compressed, irregular, or tightly interlocked with surrounding rock. In underground cavities or open fractures, however, crystals sometimes grow more freely and develop the large symmetrical shapes people often associate with gemstones and mineral specimens. Some environments remain remarkably stable for long periods, allowing crystals to continue growing without major disturbance. Heated mineral-rich fluids may move gently through rock, while atoms gradually attach themselves to existing crystal surfaces. Layer after layer accumulates over time. In these calmer conditions, crystals sometimes develop clarity and geometric precision. Temperature also influences growth patterns because heat affects how quickly atoms move and bond together. If cooling happens rapidly, crystals may remain small because atoms have little time to organize into larger structures. Slow cooling often allows larger and more ordered crystals to form. This is one reason some gemstones develop underground within slowly cooling environments where stable conditions persist for long periods. Pressure adds another layer of influence because intense compression affects atomic spacing and mineral stability. Certain gemstones can form only under specific pressure conditions existing underground. Changes in pressure may alter which minerals remain stable, which structures develop, and how crystals grow over time. The Earth's interior acts almost like a vast natural laboratory where pressure and temperature guide mineral formation. Imperfections may also become part of crystal growth. Tiny changes in chemistry, trapped fluids, fractures, or variations in temperature sometimes create inclusions and internal features within gemstones. Although modern jewelry often values perfect clarity, many crystals preserve evidence of their history through these tiny internal records formed during growth underground. Light later interacts with these crystal structures in ways. Transparency, sparkle, reflection, and color are all influenced partly by the internal arrangement of atoms within the gemstone. The precision of crystal order affects how light bends, scatters, and travels through the mineral. In this sense, the beauty people admire in gemstones is directly connected to the invisible atomic organization established during formation. Scientists studying minerals often classify crystals into different systems based upon their internal geometry and symmetry. Some grow in cubic forms, others develop hexagonal or tetragonal patterns. These categories help reveal the hidden atomic organization shaping each mineral. Even though the structures are microscopic, they influence the larger crystal in highly visible ways. Nature repeatedly creates these organized forms without planning or intention. Under the correct conditions, atoms naturally settle into repeating arrangements because those structures are physically stable. Underground, where heat, pressure, chemistry, and time remain balanced over time, crystals continue growing by these quiet natural laws. Beneath mountains, deserts, forests, and oceans, minerals continue developing ordered structures within heated rock and underground cavities hidden. Atoms align into repeating patterns while crystals slowly expand by the conditions surrounding them. The Earth continues shaping gemstones through geometry, pressure, heat, and the patient order of natural crystal growth itself. Far underground, entire regions of rock exist in partially melted or fully molten states, where temperatures rise so high that solid stone begins behaving more like thick, glowing liquid than rigid ground. This molten material is known as magma, and it plays an important role in the formation of many gemstones and minerals found throughout the world. Hidden below volcanoes, deep within fractures in the crust, and inside underground chambers, magma slowly moves through the earth, carrying enormous amounts of heat, dissolved elements, and mineral building material capable of forming crystals over time. Humans standing on the surface often imagine the ground beneath them as solid and unmoving, yet underground the planet remains surprisingly active. Magma shifts slowly through the crust beneath volcanic regions. Heat rises upward from deeper layers of the earth. Rock softens under intense temperature and pressure, while underground fluids move through cracks carrying dissolved minerals. Beneath calm landscapes, geological activity continues over time. Magma forms when rock underground becomes hot enough to melt partially or completely. Different types of magma contain different mixtures of chemical elements and dissolved minerals depending upon the surrounding geology and depth of formation. Some magmas are rich in silica. Others contain larger amounts of iron, magnesium, or additional elements influencing the minerals that crystallize during cooling. Magma may begin as a hot-moving environment, yet organized crystals can emerge from it. At first, atoms within magma move freely because of the extreme temperature. But as cooling slowly begins, conditions gradually change. Atoms lose some energy and begin bonding together into stable arrangements. Small crystals start forming within the molten material, while the magma continues cooling underground. Cooling is one of the most important stages in crystal formation because it allows atoms enough stability to organize into repeating structures. If magma remains extremely hot, atoms continue moving too actively for long-lasting crystal patterns to develop properly. As temperatures slowly decrease, however, certain minerals begin crystallizing by their chemical composition and the surrounding conditions inside the magma chamber. Different minerals form at different temperatures during the cooling process. Some crystallize early, while conditions remain extremely hot underground. Others form later as temperatures continue falling. Over time, this sequence creates mixtures of minerals inside igneous rock formed from cooled magma. Certain gemstones develop during these stages when the right combination of chemistry, cooling rate, pressure, and space exists underground. The speed of cooling strongly influences crystal size. Slow cooling allows atoms more time to arrange themselves into larger organized structures. Under stable underground conditions, crystals may continue growing gradually over thousands or even millions of years. This patient growth often produces larger crystals with clearer shapes and more developed internal structure. Rapid cooling creates different results. When magma cools quickly, atoms have far less time to organize into large crystal patterns. The resulting minerals may remain small or nearly microscopic. In volcanic eruptions, where lava reaches the surface and cools rapidly in open air or water, crystal growth is often much more limited compared to slowly cooling magma trapped underground. Humans sometimes compare crystal growth in magma to freezing water under different conditions. Water placed slowly into cold conditions may form larger organized ice crystals, while sudden freezing can create smaller irregular structures. Although gemstone formation involves far more complex chemistry and much higher temperatures, The general principle remains similar because cooling rate strongly affects crystal development. Some of the most famous gemstone-producing environments on Earth formed from magma slowly cooling underground. Pegmatites, which are exceptionally coarse-grained igneous rocks, often develop when mineral-rich magma cools slowly over time. These environments may produce remarkably large crystals, including tourmaline, topaz, beryl, and additional gemstones valued for their size and clarity. Magma also transports important chemical elements through the earth. As molten rock moves underground, dissolved minerals and gases travel within it. During cooling, these materials may concentrate in certain regions or become incorporated into growing crystals. Tiny differences in magma composition can strongly influence which gemstones form within a particular environment. The underground chambers where magma cools are often hidden many miles underground. Over long periods, tectonic movement, erosion, and uplift may slowly expose these once-buried formations. Rocks that crystallized underground can appear at the surface, where humans later discover the minerals and gemstones formed within them long ago. Even though gemstones produced from magma may later appear polished and calm, their origins are closely connected to some of the hottest and most energetic environments underground. Intense heat first melts the rock. Molten material moves through underground chambers. Cooling slowly begins. Atoms organize into repeating structures, while crystals grow gradually within the fading heat of the magma itself. Beneath volcanic regions and hidden geological chambers underground, molten rock continues cooling slowly underground. Minerals begin crystallizing, while atoms settle into organized patterns within the dark underground heat. Beneath mountains, valleys, forests, and oceans, the planet continues forming gemstones through magma, cooling, and the slow emergence of crystals from molten stone itself. The size and structure of a crystal depend heavily upon how quickly its environment changes during formation. Underground, gemstones often grow slowly inside cooling magma chambers, where temperatures decrease gradually over time. In these calmer geological settings, atoms have more opportunity to organize themselves into larger and more orderly crystal structures. Yet when cooling happens rapidly, the process changes dramatically. Crystals may remain small because the molten material solidifies before large organized patterns can fully develop. Temperature influences nearly a stage of crystal formation because heat controls how actively atoms move within magma and mineral-rich fluids. At extremely high temperatures, atoms move energetically through molten rock and remain too unstable for long-lasting crystal structures to form. As cooling begins, however, atomic movement slows enough for bonding and organization to occur. Crystals gradually emerge as elements settle into repeating patterns shaped by chemistry, pressure, and surrounding conditions. Small differences in cooling rate can change the final appearance of underground rock. Slow cooling underground may produce large visible crystals, growing over thousands or millions of years. Faster cooling closer to the surface often creates much finer grained rock filled with tiny crystals too small to see easily with the eye. Both environments may contain the same chemical elements, yet the resulting mineral structures can appear entirely different because of cooling conditions alone. Humans encounter similar effects in everyday life when liquids cool or solidify at different speeds. Melted sugar, forming rock candy, develops large visible crystals when cooling slowly and steadily. Frost spreading quickly across glass during sudden cold weather often creates much finer patterns. Although gemstone formation involves vastly greater temperatures and deep timescales, nature still follows the same general principle. Time and stability allow larger organized structures to emerge. Magma composition also plays a powerful role in determining which minerals form underground. Not all magma contains the same mixture of chemical elements. Some underground magma chambers are rich in silica and lighter elements. Others contain larger amounts of iron, magnesium, or additional mineral components. These differences strongly influence which gemstones and minerals become capable of crystallizing during cooling. Certain gemstone families form only in specific environments because they require unusual combinations of chemistry and temperature. Beryl, the mineral family including emerald and aquamarine, depends upon the presence of beryllium, which is relatively uncommon in the Earth's crust. Tourmaline forms through highly complex chemistry involving multiple elements. Topaz develops under particular conditions involving fluorine-rich environments. Gemstone records something unique about the underground setting where it formed. Underground magma chambers often remain hidden for long periods before humans ever discover the rocks formed within them. These chambers cool gradually, while surrounding rock insulates the heat, slowing the loss of temperature over time. During this long cooling process, crystals continue growing underground, while tectonic forces slowly reshape the landscape above. Rapid cooling usually occurs in environments where molten rock reaches the surface through volcanic eruptions or shallow underground fractures. Lava exposed to cooler air or water loses heat quickly, limiting the time available for large crystal growth. In some volcanic rocks, crystals remain so tiny they are difficult to identify without magnification. The speed of cooling essentially freezes the mineral structure before larger crystals can fully develop. Slowly cooled underground formations can produce crystal size. In rare environments, crystals several feet long may grow inside large underground cavities or pegmatites. These giant crystals form because conditions remain stable for exceptionally long periods, while mineral-rich fluids and slowly cooling magma continue supplying material for growth. Nature builds these structures, atom by atom, over stretches of time, almost impossible for humans to imagine fully. Cooling does not simply determine crystal size, it also influences internal structure, clarity, and mineral arrangement within the rock itself. Under stable conditions, crystals often develop more ordered structures and clearer geometric forms. Rapid environmental changes may interrupt growth, create fractures, or trap additional minerals within the crystal. Gemstone preserves evidence of the environment that shaped its formation. The underground world where these processes unfold is always changing, even though humans rarely witness it directly. Magma slowly rises through the crust. Tectonic plates shift over millions of years. Mountains form and erode. Heat moves upward from underground, while minerals crystallize within slowly cooling rock chambers hidden underground. Beneath calm landscapes, geological activity continues endlessly. Scientists studying igneous rocks often examine crystal size carefully because it reveals important clues about cooling history. Large crystals usually suggest slow underground cooling over time. Tiny crystals often indicate rapid cooling near the surface. The structure of the rock itself becomes a record of ancient conditions preserved long after the original magma solidified. Another reason gemstones formed underground appear so is because their growth required such precise combinations of time, chemistry, heat, pressure, and cooling stability. The Earth does not create these crystals quickly. Many gemstones form through patient geology unfolding across deep time while hidden. Tonight, far below mountains, deserts, forests, and oceans, underground magma chambers continue cooling slowly underground. Atoms settle into organized patterns, while crystals grow in darkness beneath layers of stone. Some crystals remain tiny from rapid cooling near volcanic regions. Others continue expanding over deep within the hidden heat of Earth. Some gemstones form through slow cooling magma or mineral-rich fluids moving through underground rock, yet other gemstones require conditions far more extreme. Among the most famous examples are diamonds, crystals formed under immense pressure, the Earth's mantle far below the crust where humans live. Unlike many surface minerals, diamonds begin their existence in one of the harshest environments on the planet, hidden beneath miles of rock in regions so deep and hot that ordinary materials behave in entirely different ways. The Earth's outer crust, although enormous from a human perspective, is actually thin compared to the full size of the planet. Beneath the crust lies the mantle, a vast region extending thousands of miles downward into the Earth. Temperatures within the mantle rise to levels, while pressure increases immensely from the tremendous weight of rock above. It is within certain regions of this deep mantle environment that diamonds are believed to form. Pressure inside the mantle is almost impossible to imagine in human terms. Miles upon miles of rock compress material from a direction. At these depths, atoms are forced together under conditions far beyond anything naturally experienced at the surface. Heat also remains extremely intense, creating environments where only specific crystal structures can survive and remain stable over long geological periods. Diamonds form primarily from carbon, one of the most important elements found throughout nature. Carbon exists in many forms across the Earth. It appears in plants, animals, graphite, coal, and countless chemical compounds. Yet under the immense pressure deep within the mantle, carbon atoms may bond together in a different arrangement, forming the tightly connected crystal structure recognized as diamond. The structure of diamond is one of the strongest natural atomic arrangements known. Each carbon atom bonds firmly with surrounding atoms in an organized repeating pattern extending throughout the crystal. This tight structure gives diamond its hardness and durability. Although diamonds are often admired for beauty and sparkle, their physical strength is deeply connected to the extreme conditions under which they formed underground. Humans sometimes compare diamond formation to materials being transformed under immense compression, though no everyday comparison truly captures the scale of geological pressure involved. Even the strongest industrial presses produce only tiny fractions of the natural pressure existing deep inside the mantle. Nature creates diamonds through conditions that humans can only partially reproduce in carefully controlled laboratory environments. Diamond formation requires precise conditions. Heat alone is not enough. Pressure alone is not enough. The environment must contain the correct combination of temperature, depth, chemistry, and stability over time. If conditions change too much, carbon may form entirely different substances rather than diamond. geological balance becomes essential for the crystal structure to develop properly. The mantle itself is not a calm or empty place. Although solid overall, parts of the mantle move slowly over time through enormous convection currents driven by heat rising from deeper underground. Rock may gradually shift, sink, or rise across long periods. Within this hidden world, diamonds slowly form while remaining trapped far below the crust for millions or even billions of years. Many diamonds discovered at the surface today are extraordinarily ancient. Some began forming more than 1 billion years ago, long before modern continents reached their present shapes. Others may be even older, preserving evidence of deep Earth conditions from periods far earlier in the planet's history. A natural diamond therefore carries a hidden geological story reaching back through long periods. Although diamonds form in the mantle, they do not always remain there. Geological activity later transports some of these crystals upward through violent volcanic processes capable of carrying deep mantle material toward the surface. Without this movement, humans would likely never encounter natural diamonds at all, because the crystals would remain permanently buried underground. The journey upward is itself extraordinary. Special volcanic eruptions originating underground can carry mantle rock rapidly upward through narrow channels. These eruptions create formations known as kimberlite pipes, which sometimes contain diamonds transported from great depth. The speed of this upward movement is important because diamonds may become unstable if exposed too long to different pressure and temperature conditions during ascent. Scientists study diamonds carefully because they preserve valuable information about the deep mantle where direct human exploration is impossible. Tiny mineral inclusions trapped inside diamonds may record pressure, temperature, and chemical conditions existing underground long ago. In this way, diamonds become natural geological records carried upward from hidden regions underground. Although diamonds are often associated with jewelry and polished brilliance, their origins are connected to immense forces operating in darkness beneath miles of stone. Extreme pressure compresses carbon atoms into tightly bonded structures, while deep mantle heat shapes the environment surrounding them. Over long periods, crystals slowly develop within one of the harshest natural settings found anywhere on Earth. Tonight, far below mountains, oceans, deserts, and forests, deep within the hidden mantle, carbon atoms continue bonding under pressure and heat. In darkness beneath miles of rock, diamonds slowly form within the restless interior of the Earth, growing through forces far older than human history. Deep within the mantle beneath the Earth's crust, diamonds form under conditions so unusual that they remain among the rarest natural crystal environments on the planet. The combination of pressure, temperature, chemistry, and depth required for diamond formation exists only within certain regions of the deep Earth. Even though carbon itself is common throughout nature, the precise conditions capable of transforming carbon into diamond are far less common. This rarity is one reason natural diamonds have fascinated humans for thousands of years. The strength of diamond begins with its internal structure. Inside the crystal, carbon atoms bond together in an extremely tight repeating arrangement where each atom connects firmly with neighboring atoms in multiple directions. This creates a stable three-dimensional framework extending throughout the crystal. The structure is so strong that diamonds resist scratching, from nearly a naturally occurring material found on Earth. Humans often describe diamond as the hardest natural substance, yet hardness has a specific meaning in geology. It refers to resistance against scratching or abrasion, rather than toughness against breaking. Diamond's tightly bonded atomic arrangement makes it exceptionally difficult for other materials to disrupt or scratch the surface. This strength originates entirely from the crystal structure created under immense mantle pressure underground. Pressure shapes crystal structure by forcing atoms into arrangements that would not normally exist near the surface. Underground, carbon atoms are compressed together under conditions of force, while intense heat allows atomic movement and bonding. Under these conditions, the tightly connected diamond structure becomes stable and capable of growing over long geological periods. Without sufficient pressure, carbon forms other materials rather than diamond. Depth is essential because the required pressure exists only far beneath the Earth's surface. Most natural diamonds are believed to form at depths of roughly 100 miles or more within the mantle. At shallower depths, pressure is usually too low to support stable diamond formation over time. The immense weight of overlying rock becomes one of the critical ingredients shaping the crystal structure. Temperature also matters greatly during formation. Conditions deep in the mantle are extremely hot, yet not a high-temperature environment produces diamonds. The balance between heat and pressure must remain within a relatively narrow range. If temperatures become too high relative to pressure, the crystal structure may not remain stable. Geological conditions therefore need to stay remarkably balanced for diamond growth to continue. Diamond-forming environments are often isolated from the surface world above. While weather changes, oceans move, forests grow, and civilizations rise and disappear at the surface, diamonds may remain buried deep within the mantle untouched for hundreds of millions or even billions of years. Their growth unfolds in darkness beneath conditions humans cannot directly observe. Scientists believe some diamonds formed during the early history of the Earth, when the planet's interior was even hotter and more active than today. Certain ancient diamonds preserve chemical evidence from periods long before complex life existed on land. In this way, diamonds act almost like time capsules, carrying hidden information from deep Earth environments across unimaginable spans of deep time. The rarity of natural diamond formation also depends upon the unusual geological events required to transport the crystals upward toward the surface. Even if diamonds form successfully deep in the mantle, they remain inaccessible unless volcanic activity carries them upward rapidly enough to preserve the crystal structure. Most regions of the Earth never experience the specific volcanic conditions capable of delivering diamonds close enough to the surface for discovery. Pressure not only shapes the strength of diamond, but also influences the crystal's overall geometry. Under stable growth conditions, diamonds may develop recognizable crystal forms with smooth, flat surfaces arranged by their internal atomic symmetry. Phase and angle reflects the repeating structure hidden inside the crystal itself. The visible geometry becomes a direct expression of atomic order created underground. Humans often admire polished diamonds for their brilliance and light reflection, yet these optical qualities also depend partly upon the crystal structure formed in the mantle. The tightly arranged atoms influence how light bends and travels through the gemstone. Sparkle, reflection, and brilliance therefore connect directly to the hidden atomic organization established during formation far below the crust. The mantle environment where diamonds form is not peaceful or motionless despite the long timescales involved. Heat continues moving upward from deeper regions of the Earth. Rock shifts slowly through mantle convection. Tectonic plates move across the surface, while deeper forces reshape the planet gradually over millions of years. Diamonds develop within this restless hidden world, beneath layers of rock impossible for humans to penetrate directly. Diamonds represent a balance between stability and geological violence. Their crystal structure forms slowly under stable, deep mantle conditions, yet volcanic eruptions later transport them upward through powerful explosive events. Calm growth and violent movement both become part of the diamond's long geological journey. Beneath mountains, continents, deserts, forests, and oceans, carbon atoms continue bonding under immense mantle pressure hidden deep below the crust. In darkness beneath miles of heated rock, diamonds slowly develop their crystal structures through rare conditions existing only within the deep interior of Earth. Not all gemstones form from cooling magma or deep mantle environments. Some develop through a different geological process known as metamorphism, where existing rocks are slowly transformed by heat, pressure, and chemical change underground. In these environments, minerals already present inside rock begin reorganizing themselves as conditions grow more extreme. Over long periods of time, entirely new crystal structures may emerge, while older minerals disappear or transform into something different. Hidden beneath mountain ranges and shifting tectonic plates, rocks change form through one of the most powerful processes operating inside Earth. The word metamorphic comes from ancient language meaning transformation or change, which describes the process well. Existing rocks do not simply melt during metamorphism. Instead, they are altered gradually while remaining mostly solid. Heat increases atomic movement inside the minerals, while pressure compresses the rock from multiple directions. Under these conditions, atoms begin reorganizing themselves into structures more stable for the environment. Humans sometimes compare metamorphism to baking clay in a kiln or transforming ingredients slowly under heat and pressure. Although the geological process is vastly more complex and unfolds over millions of years, the general idea remains similar because materials change structure when exposed to new environmental conditions over time. Inside the Earth, rock itself slowly transforms while minerals reorganize underground. Pressure plays a major role in metamorphic environments because tectonic forces constantly reshape the crust. When continents collide, enormous sections of rock may become buried beneath rising mountain ranges. Layers of crust are compressed, folded, and pushed downward while temperatures continue rising with depth. Minerals trapped within these environments experience conditions different from those present when the rock first formed. Heat also contributes strongly to metamorphic change. As buried rock sinks deeper into the crust, temperatures gradually increase. Existing minerals may become unstable under the new conditions and begin reorganizing their atomic structures into different arrangements. New crystals form, while older mineral patterns disappear or transform. Over immense deep time, new rock types may emerge from the original material. Metamorphic environments often preserve evidence of enormous geological movement. Gemstones formed through metamorphism are closely connected to mountain building, tectonic collisions, and deep crustal transformation occurring over millions of years. Beneath the calm appearance of mountain landscapes, Vast sections of rock may have once been compressed, heated, and altered underground before later rising closer to the surface. Several important gemstones form through metamorphic processes. Rubies and sapphires may develop in metamorphosed rocks, rich in aluminum when conditions allow. Garnets commonly grow during metamorphism as minerals reorganize inside heated rock. Jade also forms through complex metamorphic conditions involving pressure, fluid movement, and chemical transformation. Each gemstone reflects the specific environment in which the surrounding rock was altered. Minerals reorganize during metamorphism because atomic structures stable under one set of conditions may no longer remain stable as temperature and pressure change. Atoms gradually shift into new arrangements better suited for the environment. This reorganization often occurs slowly, while the rock remains under pressure underground. Crystal structures adapt over time as geology reshapes the minerals themselves. Some metamorphic gemstones form under directed pressure, where forces compress rock more strongly from certain directions. This pressure may cause minerals to align into layers or elongated patterns within the rock. In other environments, heat dominates more strongly, allowing larger crystals to grow as atoms reorganize gradually over time. Small differences in conditions often produce different results. Water and mineral-rich fluids may also influence metamorphism by carrying dissolved elements through heated rock. These fluids can trigger chemical reactions, transport material between minerals, or support crystal growth within fractures and cavities. The underground environment becomes highly dynamic as heat, pressure, fluids, and tectonic movement interact continuously underground. Ordinary rock can transform when conditions allow. Limestone may become marble. Shale may transform into slate or schist. Existing minerals reorganize while entirely new crystals develop within the changing rock. Geological history becomes written into the structure of the transformed material itself. Scientists study metamorphic rocks carefully because they reveal important information about ancient tectonic activity and deep crustal conditions. Crystal size, mineral alignment, and chemical composition all preserve clues about pressure, temperature, and forces operating long ago beneath mountain ranges and tectonic boundaries. Metamorphic gemstones therefore carry hidden evidence of the Earth's dynamic internal processes. The timescales involved remain enormous compared to human life. While civilizations rise and disappear at the surface, buried rock may continue transforming slowly underground for millions of years. Pressure gradually reshapes mineral structures, while heat drives atomic reorganization underground. The resulting gemstones become quiet records of geological transformation unfolding across deep time. Tonight, beneath ancient mountain ranges and hidden tectonic boundaries underground, existing rocks continue changing under heat and pressure underground. Minerals reorganize while new crystal structures slowly emerge underground. Beneath forests, deserts, oceans, and valleys, the planet continues transforming stone itself through the patient forces of metamorphism. Underground, transformation rarely happens suddenly. Geological change usually unfolds with patience across long periods, while heat, pressure, fluids, and tectonic movements slowly reshape existing materials into something new. In metamorphic environments, minerals gradually reorganize themselves as surrounding conditions continue changing. over thousands, millions, and sometimes even hundreds of millions of years, ordinary rock may slowly become entirely different in structure, composition, and appearance. The gemstones produced through these processes carry the quiet history of transformation deep within their crystal structures. Heat and pressure act together as the primary driving forces behind metamorphism. As rock sinks deeper beneath mountain ranges or tectonic boundaries, temperatures steadily rise, while pressure increases from the enormous weight of overlying material. Existing minerals may become unstable under these new conditions and begin changing into different crystal forms better suited for the environment. Geological transformation, therefore, becomes a response to changing physical conditions underground. During metamorphism, the original rock does not usually disappear or melt completely. Instead, atoms reorganize slowly, while remaining mostly within solid material. Minerals gradually shift into more stable structures, while crystal growth continues over time. The process resembles a slow internal rebuilding, where the arrangement of matter changes over time underground. Humans sometimes compare metamorphism to wood slowly changing under pressure and age, or ingredients transforming gradually during long cooking processes. Although geological transformation operates on vastly larger scales and under much more extreme conditions, the central idea remains similar because materials respond to prolonged heat and pressure by reorganizing their internal structure. Inside the Earth, entire rock formations undergo this process over time. Transformation creates new minerals because different environmental conditions favor different atomic arrangements. Minerals stable near the surface may no longer remain stable deeper underground, where temperatures and pressures are much higher. Atoms begin forming new crystal structures, while older minerals break down or reorganize themselves into different forms. Over time, entirely new mineral combinations emerge from the original material. The surrounding environment strongly influences the final results of metamorphism. Slight differences in temperature, pressure, fluid chemistry, or burial depth may produce different minerals even within neighboring regions underground. Some environments favor the growth of garnets, others support jade formation or the development of corundum crystals that later become rubies and sapphires. Geological conditions act almost like instructions guiding transformation underground. Water and mineral-rich fluids often play an important supporting role during metamorphism. Heated fluids moving through cracks and rock layers can transport dissolved elements between minerals while encouraging chemical reactions and crystal growth. Fluids help introduce entirely new elements into the rock, altering the minerals that develop. The underground environment becomes a complex system where heat, pressure, chemistry, and movement interact continuously. Metamorphism remains gradual. Changes occurring underground are usually far too slow for humans to observe directly. A mountain range may continue evolving through tectonic pressure over millions of years, while buried rock slowly transforms underground. Crystal structures reorganize atom by atom, while forces reshape the crust above. The Earth changes through deep time rather than sudden rapid events alone. The texture of metamorphic rock often reflects the pressure conditions surrounding formation. In some rocks, minerals align into layered or ribbon-like patterns because directional pressure compresses the material more strongly from certain sides. In others, crystals grow larger and more evenly distributed under relatively stable heat-dominated environments. The appearance of the rock itself becomes a record of the forces involved in transformation. Scientists study metamorphic minerals carefully because they reveal valuable information about ancient tectonic environments, Earth's history. Crystal size, mineral composition, and structural arrangement help researchers estimate the temperatures and pressures experienced by the rock long ago. In this way, metamorphic gemstones preserve clues about conditions impossible for humans to witness directly. Some of the world's most beautiful gemstones owe their appearance to these slow underground transformations. Deep red rubies, blue sapphires, green jade, and richly colored garnets often develop within metamorphic environments shaped by pressure and heat over time. Although later admired for beauty and rarity, these crystals began as part of ordinary rock, slowly changing beneath mountain-building forces underground. The Earth itself remains dynamic and restless, even when landscapes appear calm from the surface. Continents move slowly across the planet. Crustal plates collide and sink. Mountains rise while erosion gradually wears them down again. Deep beneath these shifting landscapes, metamorphism continues altering rock and minerals through steady geological transformation hidden from view. Gemstones formed through metamorphism represent survival through change. Existing materials adapt to increasingly extreme conditions, while atoms reorganize into structures stable enough to endure environments. A crystal formed this way becomes evidence of geological transformation unfolding across deep time. Tonight, beneath mountain ranges, valleys, deserts, forests, and oceans, rocks buried underground continue changing under heat and pressure. Minerals reorganize slowly, while new crystal structures emerge atom by atom through the quiet force of metamorphism. Geological transformation continues inside the restless interior of Earth. Underground, water moves through the Earth in ways most people rarely imagine. Far below rivers, lakes, and oceans at the surface, heated water carrying dissolved minerals travels slowly through cracks, fractures, and porous rock deep within the crust. Under the right conditions, these underground fluids play a major role in the formation of crystals and gemstones. In some environments, water becomes one of the most important agents shaping mineral growth because it transports chemical elements, supports crystal formation, and allows gemstones to develop gradually within hidden cavities underground. The water involved in gemstone formation is often different from ordinary surface water. Underground, fluids may become extremely hot due to nearby magma or the natural geothermal heat rising from the Earth's interior. As temperatures increase, water gains the ability to dissolve larger amounts of minerals from surrounding rock. Elements that normally remain locked inside stone may slowly dissolve into these heated fluids and travel through underground pathways over time. Humans sometimes compare this process to sugar dissolving into hot tea more easily than cold water. Heat allows more material to remain suspended within the liquid. Underground, the same basic principle applies on a geological scale. Heated water moving through rock can carry dissolved silicon, aluminum, copper, iron, chromium, and many additional elements important for mineral formation. The Earth transports these ingredients through underground fluid systems hidden. Mineral-rich fluids move slowly through fractures created by tectonic movement, volcanic activity, or natural cracking within the rock. Some pathways extend for great distances underground, while others remain confined to small cavities or narrow veins. As these fluids travel, they interact continuously with surrounding minerals, picking up dissolved material in some regions and depositing it in others, depending upon changing conditions. Crystallization begins when environmental conditions shift in ways that reduce the fluid's ability to keep certain minerals dissolved. Temperature changes are especially important because cooling often encourages dissolved elements to leave the fluid and begin forming solid crystals. Pressure changes, chemical reactions, or evaporation within underground cavities may also trigger mineral deposition and crystal growth. Hydrothermal crystal formation can be gradual and layered. Heated fluids may continue flowing through the same underground region for long periods, while tiny amounts of mineral material accumulate slowly on crystal surfaces. Layer after layer develops, while atoms organize themselves into repeating structures by the chemistry of the environment. Some gemstones form almost entirely through these fluid-driven geological processes. Emeralds often develop in environments where mineral-rich fluids move through specific rock types containing the necessary elements for crystal growth. Quartz crystals frequently form from silica-rich fluids, cooling within underground fractures and cavities. Topaz, tourmaline, fluorite, and many additional minerals may also grow through hydrothermal activity underground. The movement of heated fluids through rock creates environments filled with ongoing chemical interaction and transformation. Water carries dissolved elements from one location to another, while heat and pressure influence which minerals remain stable. Crystals grow where conditions become favorable, while other minerals dissolve elsewhere. Beneath calm landscapes at the surface, geological chemistry continues constantly in darkness underground. Temperature shifts strongly influence crystal growth because cooling changes how dissolved material behaves within the fluid. In hotter conditions, more elements remain dissolved and mobile. As fluids cool gradually, while moving away from heat sources such as magma chambers, certain minerals begin crystallizing out of solution. Different minerals form at different temperatures, depending upon their chemistry and stability. Pressure changes can also trigger crystallization. Underground, fluids may remain under enormous pressure while moving through narrow fractures inside the crust. If the pressure decreases due to tectonic activity or expanding underground spaces, dissolved minerals may suddenly become less stable within the fluid and begin depositing onto nearby surfaces as crystals. Fluid-based gemstone formation requires patience. Crystal growth may continue slowly for thousands or millions of years, while underground conditions remain stable enough to support gradual mineral deposition. Some crystals develop transparent layers, recording changes in chemistry, temperature, or fluid movement over timescales. Scientists studying hydrothermal gemstones often examine fluid inclusions trapped inside the crystals themselves. Tiny pockets of ancient fluid, preserved during crystal growth, can reveal valuable information about the temperature, chemistry, and pressure conditions existing underground long ago. In this way, gemstones preserve microscopic records of the fluids from which they formed. The underground systems carrying these mineral-rich fluids are closely connected to broader geological activity underground. Magma heats surrounding water. Tectonic movement creates fractures for fluid transport. Heat flows upward from deep within the crust, while dissolved elements circulate through underground pathways. Gemstone formation becomes part of a much larger, interconnected geological system operating continuously underground. Tonight, beneath mountains, forests, deserts, and oceans, heated mineral-rich fluids continue moving slowly through fractures within the Earth's crust. Dissolved elements travel through darkness, while cooling temperatures and shifting conditions guide crystal growth underground. Gemstones continue forming through water, heat, chemistry, and the quiet movement of minerals through stone itself. Underground, gemstone formation often depends upon movement rather than stillness alone. Heated fluids carrying dissolved minerals travel slowly through fractures, cavities, and layers of rock, while conditions continue changing around them. As pressure shifts, temperatures rise or fall, and underground pathways open or close, minerals begin leaving the fluid and settling into organized crystal structures. Over long periods, these quiet underground movements shape the growth of gemstones hidden underground. Pressure changes influence crystallization because dissolved minerals remain stable within underground fluids only under certain conditions. Underground, heated water may exist under enormous pressure while carrying large amounts of dissolved material through narrow fractures inside the rock. Yet if pressure decreases even gradually, the fluid's ability to hold some minerals in solution may weaken. At that point, dissolved elements begin separating from the fluid and attaching themselves to nearby surfaces where crystals slowly start growing. Humans sometimes observe similar behavior in life without realizing how closely it resembles geology underground. Carbonated water, for example, holds dissolved gas under pressure inside a sealed container. Once the pressure changes after opening the bottle, bubbles begin forming and escaping from the liquid. Underground, minerals may respond somewhat similarly when pressure conditions shift, though the geological process unfolds much more slowly and involves crystal growth rather than gas release. Movement through underground rock is essential because fluids transport the raw materials needed for gemstone formation. Heated water dissolves minerals from surrounding stone while traveling through the crust. Elements such as silicon, aluminum, copper, chromium, iron, and additional chemical components move through fractures over time. Without this movement, many gemstones would never receive the ingredients required for crystal growth. Deposition occurs when dissolved minerals leave the fluid and begin forming solid crystal structures. Tiny amounts of material settle onto existing surfaces layer by layer, while atoms organize themselves into repeating patterns. Growth may begin on the walls of underground cavities, along fractures inside rock, or around small mineral seeds already present in the environment. Over time, these deposits expand gradually into larger crystal formations. Underground crystal growth is highly sensitive to changing conditions. A small temperature drop, pressure shift, or chemical change may alter which minerals begin crystallizing from the fluid. Some crystals grow rapidly for a period before stopping entirely when conditions change again. Others continue developing slowly over timescales, while the underground environment remains stable. Water supports gemstone formation not only by transporting minerals, but also by creating conditions favorable for atomic organization and crystal growth. Heated fluids allow elements to move more freely through the crust compared to solid rock alone. This mobility gives atoms opportunities to gather, bond, and form increasingly organized structures within underground spaces where crystals can expand gradually. Some environments become especially rich in mineral deposition because fluid movement continues repeatedly through the same pathways over time. Heated water may circulate through fractures near magma chambers while cooling gradually as it moves outward. As conditions change along the pathway, minerals begin depositing at different locations depending upon temperature, pressure, and chemistry. Over deep time, these repeated cycles build crystal-rich veins and gemstone-bearing formations hidden. Movement also shapes crystal appearance because flowing fluids deliver minerals unevenly across growing surfaces. Changes in fluid chemistry may create visible layers, color zones, or internal patterns within the gemstone itself. Tiny variations preserved during growth become geological records of the changing underground environment where the crystal formed. Scientists often study mineral veins created through hydrothermal deposition because these formations preserve evidence of ancient underground fluid systems. Quartz veins, for example, commonly develop when silica-rich fluids move through fractures and gradually deposit crystal material over time. Other gemstone-bearing veins may contain combinations of minerals reflecting the chemistry of the fluids that once circulated through them deep within the crust. Pressure changes underground occur for many reasons. Tectonic movement may compress or stretch sections of crust. Magma rising underground can alter surrounding stress conditions. Rock fractures may suddenly open new pathways for fluid movement. Erosion at the surface can slowly reduce pressure on buried formations over millions of years. The underground environment therefore remains dynamic rather than static, with forces continuously reshaping conditions for crystal growth. Gemstone formation through fluids requires patience. Crystals may grow atom by atom, while underground water systems continue transporting dissolved minerals through darkness underground. Human civilizations may rise and disappear, while a single crystal continues expanding slowly inside a hidden cavity underground. The Earth itself behaves almost like a vast interconnected system of movement and transformation. Heat flows upward from deep interior regions. Fluids circulate through fractures. Minerals dissolve and crystallize repeatedly. Pressure changes reshape underground pathways, while tectonic forces slowly alter the crust above. Gemstones emerge through this continuous geological activity unfolding over time. Tonight, beneath mountains, valleys, forests, deserts, and oceans, heated fluids continue carrying dissolved minerals through hidden fractures underground. Pressure shifts guide crystallization, while atoms settle into growing structures underground. Crystals continue forming through movement, deposition, water, and the quiet geological circulation of Earth. Underground, even the most perfectly formed crystals require one important condition in order to grow properly: space. Without room to expand, crystals often remain small, crowded, or tightly locked inside surrounding rock. Yet when underground cavities, fractures, or hollow spaces develop underground, crystals may grow far more freely over time. Inside these hidden chambers, minerals carried by heated fluids slowly attach themselves to surfaces, while gemstones and crystal formations expand in darkness underground. Crystal growth depends heavily upon the environment because atoms need physical room to organize into repeating structures. In tightly compressed rock, where minerals compete for limited space, crystals may remain irregular or interwoven with neighboring grains. In more open underground settings, however, crystals can develop clearer shapes with flat surfaces, pointed tips, and symmetrical geometry reflecting their internal atomic order. Humans sometimes compare this process to plants growing in different conditions. A tree crowded tightly among obstacles may twist and compete for space, while a tree growing in an open field can expand more evenly outward. Crystals behave somewhat similarly underground, because open environments allow more organized and unrestricted growth over long geological periods. A geode is one of the most fascinating environments for crystal formation. A geode is a hollow cavity inside rock, where crystals line the interior surfaces like hidden chambers filled with mineral growth. From the outside, geodes may appear ordinary and rough, yet inside they often contain crystal formations developed slowly over time. Geodes form through several geological processes, depending upon the surrounding rock and environment. Some begin as gas bubbles trapped inside cooling volcanic rock. Others develop through cavities created by dissolving minerals or shifting geological activity underground. Once the hollow space exists, mineral-rich fluids moving through the surrounding rock may gradually deposit crystals along the inner walls of the cavity. As heated fluids enter the open space, dissolved minerals begin attaching themselves to available surfaces where crystallization becomes possible. Layer after layer accumulates slowly, while atoms organize into repeating structures. Over thousands or millions of years, crystal points may extend inward from the cavity walls, while maintaining the symmetry and geometry determined by their mineral structure. Quartz geodes are among the most familiar examples. Silica-rich fluids moving through underground cavities slowly deposit quartz crystals along the interior surfaces. Over immense periods, transparent or colored crystal points continue growing inward, while the hollow center remains open. When discovered and opened by humans, the inside may reveal glittering crystal formations hidden within ordinary stone. The open space inside geodes is extremely important because it allows crystals to expand freely without being compressed tightly by surrounding rock. This freedom often produces larger, sharper, and more symmetrical crystal forms than those developing in crowded environments underground. Space itself becomes part of the conditions guiding gemstone growth. Growth continues only as long as the environment remains favorable. Mineral-rich fluids must continue delivering dissolved material. Temperatures and pressures must remain within ranges supporting crystal stability. Underground pathways allowing fluid circulation must stay open. If conditions change too dramatically, crystal growth may slow, stop, or shift toward entirely different minerals. Geodes remain hidden for most of their existence. Entire crystal-lined chambers may rest underground for millions of years, untouched, beneath deserts, forests, volcanic fields, or ancient rock layers. Long before humans ever discover them, crystals continue growing in darkness inside these sealed geological spaces. Different minerals create different appearances within geodes and underground cavities. Some develop long needle-like crystals, while others form blocky geometric shapes or layered mineral coatings. Color may vary depending upon trace elements present during growth. Iron can create reddish tones. Manganese may produce pink coloration. Tiny chemical differences inside the fluid influence the final appearance of the crystals lining the cavity walls. Scientists often study geodes and crystal cavities because they preserve detailed records of ancient underground conditions. Layering patterns, crystal shapes, fluid inclusions, and mineral sequences reveal information about temperature, chemistry, fluid movement, and geological activity during formation. These underground chambers become natural archives, recording the slow processes shaping the Earth underground. The timescales involved in cavity crystal growth remain immense compared to human experience. A crystal lining inside a geode may require hundreds of thousands or even millions of years to reach full size. During that time, mountains may erode, climates may shift, and entire ecosystems may change at the surface, while hidden growth continues within the sealed cavity. Geodes also show a strong contrast between exterior and interior appearance. From the outside, many geodes appear rough, plain, or unremarkable, yet hidden inside may be delicate crystal structures formed through geological patience. Nature builds beauty underground, where no sunlight reaches, and no human eyes observe the process for long periods. Tonight, beneath volcanic rock, mountain layers, deserts, forests, and ancient stone hidden deep underground cavities continue supporting crystal growth underground. Mineral-rich fluids move slowly through fractures, while crystals expand into open spaces in darkness underground. Geodes and hidden chambers continue filling with gemstones and crystal formations shaped through space, time, and quiet geological growth itself. Underground, crystal growth continues only while the environment remains stable enough to support it. Heat, pressure, chemistry, fluid movement, and available space must remain balanced over time for gemstones to expand gradually into larger and more organized structures. If underground conditions shift too suddenly, growth may slow, stop, fracture, or change direction entirely. Yet in rare environments where stability persists for long periods, crystals may continue developing underground for thousands, millions, or even billions of years. The size of a crystal depends greatly upon time, because crystal growth is usually extremely slow. Atoms attach themselves layer by layer to existing crystal surfaces, while repeating patterns continue extending outward. In some environments, growth may occur so gradually that only microscopic changes happen over many human lifetimes. Geological time moves differently from human time, and crystals reflect that immense patience through their slow formation underground. Environment also shapes crystal size, because different conditions support different rates of growth. A crystal developing within a crowded section of rock may remain small due to limited space and unstable conditions. Another crystal growing inside a large underground cavity, supplied continuously with mineral-rich fluids, may expand far more freely over time. Space, chemistry, temperature, and pressure all combine to influence how large a gemstone can become. Humans sometimes compare crystal growth to the formation of icicles during winter. Water freezes layer by layer, while conditions remain cold enough for gradual accumulation. If temperatures rise suddenly, growth stops or begins melting. Underground crystal formation operates through much slower and more complex geology, yet the basic idea remains similar because stable conditions allow gradual ordered expansion over time. Crystal structure remains highly organized as growth continues. New atoms joining the crystal do not attach randomly. Instead, they align by the existing atomic pattern already present within the mineral. The crystal essentially guides its own growth, through the repeating structure established during the earlier stages of formation. This repeating order explains why crystals often develop recognizable geometric forms. Quartz commonly forms six-sided structures. Pyrite may develop cubic shapes. Garnets often grow into symmetrical dodecahedral forms. The external appearance reflects the hidden atomic arrangement extending throughout the crystal itself. Growth follows natural mathematical patterns shaped by chemistry and physical laws underground. Even when crystals become large, their internal structure often remains astonishingly consistent. Under stable conditions, atoms continue aligning in the same repeating arrangement over time. This ordered growth creates smooth crystal faces, sharp edges, and symmetrical forms admired by both scientists and collectors. Nature produces geometric precision underground without intention or design. Some environments allow exceptionally large crystals to form because conditions remain favorable for lengths of time. Giant gypsum crystals discovered within underground caves in Mexico reached enormous sizes due to stable heat, mineral-rich fluids, and long uninterrupted growth periods. Other large crystals found around the world formed under similarly rare conditions, where geological balance persisted for long periods. Growth patterns may also preserve evidence of environmental changes occurring during formation. Variations in fluid chemistry, temperature, or mineral supply sometimes create bands, layers, or zones within the crystal itself. These internal patterns become geological records of the changing underground environment where the gemstone developed. Scientists often study these structures carefully to understand the conditions shaping crystal growth long ago. Space remains one of the most important requirements for crystal development because open environments allow crystals to expand freely outward while maintaining symmetrical forms. Underground cavities, fractures, and geodes provide opportunities for larger and more defined crystal growth compared to crowded rock interiors where minerals compete for limited room. The underground world supporting crystal growth is never motionless, even though the process unfolds slowly. Heated fluids continue circulating through fractures. Pressure shifts gradually as tectonic forces reshape the crust. Temperatures change with depth and nearby geological activity. Minerals dissolve in some places while crystallizing in others. Beneath still landscapes at the surface, geological systems remain active continuously over time. Crystal growth shows how natural laws repeatedly produce order from simple atomic interactions. Atoms bond by chemistry and physical structure, while environmental conditions guide the process. Over long periods, these repeating patterns generate crystals of complexity and beauty hidden. Scientists often describe crystal formation as a balance between stability and change. Conditions must remain stable enough for ordered growth, while geological processes continue supplying heat, fluids, dissolved minerals, and space. Too much disruption prevents organized crystal development. Too little geological activity may limit mineral transport and chemical interaction. Gemstone formation depends upon this delicate underground balance unfolding across deep time. Tonight, beneath mountains, forests, deserts, volcanic fields, and ancient stone hidden underground, crystals continue growing wherever conditions remain favorable underground. Atoms align into repeating structures, while gemstones expand through time beneath layers of rock. Crystal growth continues by quiet natural patterns shaped by space, chemistry, heat, and the immense patience of deep time itself. Color is gemstones, deep blue sapphires, rich green emeralds, glowing red rubies, golden topaz, violet amethyst, and countless other gemstones display colors so striking that humans have admired them for thousands of years. Yet the thing is that many gemstone colors come not from the primary mineral itself, but from tiny impurities hidden within the crystal structure. In geological terms, these impurities are often small amounts of additional elements incorporated into the crystal during growth underground. The word impurity may sound negative in life, yet in gemstones these tiny additions often create the qualities people value most. A pure crystal may sometimes appear nearly colorless or transparent. Small traces of iron, chromium, titanium, manganese, copper, or additional elements can alter the way light behaves inside the crystal and produce colors visible to the eye. Rubies provide one of the most famous examples of this process. The mineral corundum, when chemically pure, is generally colorless. Yet when tiny amounts of chromium become incorporated into the crystal structure during growth, the gemstone develops the deep red color associated with ruby. Sapphires belong to the same mineral family, but different trace elements such as iron and titanium may produce blue coloration instead. Emeralds form through similar geological principles. The mineral beryl becomes richly green when trace amounts of chromium or vanadium enter the crystal during formation. Without those additional elements, the crystal would appear entirely different. The beautiful colors admired in gemstones therefore depend heavily upon tiny chemical variations introduced underground during crystal growth. Humans sometimes compare this effect to adding small amounts of dye into clear water. Even tiny quantities can dramatically change appearance. Inside gemstones, however, the process is far more complex because trace elements become part of the crystal structure itself, while the gemstone forms atom by atom underground. The color becomes woven directly into the mineral's internal arrangement. These trace elements usually enter the crystal because they are present in the surrounding environment during formation. Heated fluids, magma, or metamorphic conditions may carry dissolved elements through underground rock, while crystals grow gradually within cavities or mineral-rich environments. As atoms bond into repeating structures, small amounts of additional elements may become trapped within the growing crystal. The crystal structure itself strongly influences how color appears because light interacts with the gemstone by the arrangement of atoms inside it. When light enters a crystal, certain wavelengths may be absorbed, while others pass through or reflect outward. The remaining visible wavelengths create the color humans perceive. In this way, gemstone color depends upon both chemical composition and crystal structure working together. Tiny chemical differences can create enormous visual changes in gemstones. A crystal containing only trace amounts of one additional element may appear vivid blue, green, or red, compared to another crystal of nearly identical composition that remains pale or colorless. Geological chemistry operates with sensitivity during gemstone formation underground. Light itself plays a central role in revealing gemstone color. Without light, the internal chemistry and structure would remain invisible to human eyes. When light enters the crystal, it interacts with electrons inside the atoms making up the gemstone. Certain energies are absorbed, while others continue outward toward the observer. The colors visible in gemstones are therefore partly the result of physical interactions between light and matter occurring inside the crystal structure. Some gemstones even change appearance under different lighting conditions because various wavelengths interact differently with the crystal. Others display color zoning, where changing conditions during growth created visible bands or variations within the gemstone itself. These internal patterns preserve records of shifting geological chemistry during formation underground. The purity and transparency of a crystal also influence how color appears. In highly transparent gemstones, light may travel deeply through the structure before reflecting outward, producing rich, vivid appearance and brilliance. In more opaque minerals, color may appear softer or more diffuse, depending upon how light moves through the crystal. Scientists study gemstone coloration carefully because trace elements reveal valuable information about the environment where the crystal formed. The presence of chromium, iron, copper, manganese, or additional elements may indicate specific rock types, fluid chemistry, or temperature conditions existing during growth underground. In this way, gemstone color becomes part of the history preserved within the crystal. Nature creates gemstone color through chemistry and physics over time. No painter applies the color. No deliberate design exists. Tiny atomic differences and light interactions generate beauty underground through natural geology alone. The environments where gemstones form are filled with chemical variation. Mineral-rich fluids move through fractures carrying dissolved elements. Magma cools while different minerals crystallize. Pressure and temperature alter existing rock. During these processes, trace elements become incorporated into growing crystals, shaping the colors later admired at the surface. Tonight, beneath mountains, deserts, forests, volcanic regions, and ancient stone hidden far below the crust, crystals continue forming underground, while trace elements shape their color. Light will someday reveal these hidden chemical patterns after immense deep time has passed. Gemstones continue growing in darkness, while chemistry and crystal structure prepare the colors hidden within them. The variety of colors found in gemstones comes from a delicate interaction between chemistry, crystal structure, and light. Tiny differences deep within a crystal can change the way a gemstone appears to the eye. A trace amount of iron may create soft green tones in one mineral, while chromium may produce vivid red in another. Copper can generate bright blue coloration in certain stones, while manganese may create pink or violet shades depending upon the surrounding crystal environment. Underground, these small chemical variations shape the diversity later revealed in sunlight. Different elements influence gemstone color because atoms interact with light in different ways. When light enters a crystal, parts of the light spectrum may be absorbed by electrons within certain elements, while other wavelengths continue traveling outward. The colors humans see are the wavelengths that remain visible after this interaction takes place inside the gemstone. Humans often think of color as something resting directly on the surface of an object. Yet gemstones reveal that color can emerge from processes happening deep inside matter itself. Light entering a crystal interacts with atomic structure, trace elements, and internal organization before returning to the eye. The visible appearance becomes a combination of chemistry and physics operating together inside the gemstone. Crystal structure strongly affects this process because the arrangement of atoms influences how light moves through the mineral. Even gemstones containing similar trace elements may display different colors, if their crystal structures differ. The organization of the crystal changes how electrons respond to incoming light and which wavelengths become absorbed or transmitted outward. Corundum, the mineral family including ruby and sapphire, shows this clearly. The basic crystal structure remains nearly the same, yet different trace elements create entirely different appearances. Chromium may produce red ruby, while combinations involving iron and titanium can create blue sapphire. The same mineral framework therefore becomes capable of variation depending upon the chemical environment during formation. Variation itself is one of the defining features of gemstone formation. No two environments are perfectly identical. Temperature, pressure, fluid chemistry, cooling rate, and surrounding rock all influence which elements become incorporated into a growing crystal. Even small changes during formation may create noticeable differences in color, transparency, or internal patterning. Some gemstones contain visible color zones because conditions shifted while the crystal continued growing underground. A changing supply of trace elements or gradual environmental changes may produce bands, layers, or uneven coloration within the stone itself. These patterns become geological records of the crystal's growth history, preserved deep inside the structure. Light behavior also shapes how humans perceive gemstones after they are discovered and exposed to the surface world. Transparent crystals may allow light to pass deeply through the stone before reflecting outward, creating brilliance and internal glow. Other gemstones scatter light more softly through microscopic structures or inclusions, producing velvety or shimmering effects depending upon the mineral. Certain gemstones display especially unusual optical behavior because of their crystal structure and internal chemistry. Opal can produce shifting flashes of color through microscopic internal patterns interacting with light. Labradorite displays glowing blue and green flashes caused by light scattering within layered crystal structures. Alexandrite may appear green under one type of light and reddish under another due to complex absorption behavior involving chromium inside the crystal. Scientists studying gemstones often examine light interaction carefully because optical behavior reveals valuable information about internal structure and composition. Specialized instruments measure how crystals absorb, reflect, and transmit different wavelengths of light. These patterns help identify minerals and reveal the trace elements present within the gemstone itself. One aspect of gemstone color is how geological chemistry operating invisibly underground creates emotional and visual responses in human observers. Tiny atomic variations formed underground may later produce colors associated with calmness, warmth, mystery, luxury, or beauty. Ancient civilizations often assigned symbolic meaning to gemstones long before understanding the chemistry responsible for their appearance. The environments shaping gemstone color remain highly dynamic over time. Heated fluids move through fractures carrying dissolved elements. Magma cools, while minerals crystallize in changing chemical conditions. Metamorphic pressure alters existing rock, while trace elements become incorporated into growing crystals, atom by atom. Gemstone records part of this hidden geological activity through its appearance. The visible beauty of gemstones depends upon invisible structure. Atomic organization, trace chemistry, and light interaction all combine underground of the crystal itself. The colors humans admire are ultimately expressions of geology unfolding underground across deep time. Even after gemstones reach the surface, their appearance continues depending upon light. Sunlight, candlelight, firelight, and artificial illumination may reveal different aspects of the same crystal, because changing wavelengths interact differently with the mineral structure. The gemstone remains connected to the physics of light long after leaving the environment where it formed. Tonight, beneath mountains, deserts, forests, volcanic regions, and ancient layers of stone hidden far below the crust, crystals continue growing, while trace elements shape their future appearance, atom by atom. In darkness underground, chemistry and crystal structure prepare the colors that light will someday reveal, after immense deep time has passed underground itself. For most of their existence, gemstones remain hidden, far from sunlight, weather, plants, animals, and human life. Crystals may spend millions or even billions of years buried beneath layers of rock, while geological processes continue shaping the earth around them. Yet eventually, some gemstones begin a journey upward toward the surface through volcanic activity, tectonic uplift, erosion, and shifting crustal movement. Without these powerful forces, most gemstones would remain permanently inaccessible underground. Volcanic activity plays one of the most important roles in transporting certain gemstones upward from environments. Beneath volcanic regions, magma rises through fractures and channels within the crust while carrying heat, gases, minerals, and sometimes crystals formed at great depth. These eruptions connect the hidden interior of the Earth with the surface world above in dramatic and powerful ways. Diamonds provide one of the clearest examples of this process. Although diamonds form deep within the mantle under immense pressure, they reach the surface only because special volcanic eruptions transport them upward through narrow geological structures called kimberlite pipes. These eruptions originate far deeper than ordinary volcanic activity and move material upward with tremendous speed. The speed of transport is important because diamonds remain stable only under certain conditions. If they rise too slowly or remain exposed too long to lower pressure environments underground, the crystal structure may gradually change into other forms of carbon. Rapid volcanic transport helps preserve the diamonds during their journey from the mantle toward the crust and closer to the surface. Volcanic eruptions can also transport many additional minerals and gemstones formed within magma chambers or surrounding rock. Crystals growing underground may become trapped inside rising molten material and carried upward through volcanic systems. Over immense deep time, these eruptions help redistribute deep earth minerals closer to regions where humans may discover them. Humans often think of volcanoes mainly as destructive forces because eruptions can reshape landscapes dramatically in short periods. Yet from a geological perspective, volcanic systems also act as pathways connecting environments with the surface. They move heat, gases, minerals, and crystals upward while constantly reshaping the crust over millions of years. Geological uplift also exposes gemstones gradually over time. Tectonic forces pushing sections of crust upward may slowly raise once buried rock closer to the surface. Mountain ranges often contain rocks that originally formed underground before later uplift exposed them through enormous geological movement. Crystals hidden within those rocks become accessible as erosion removes overlying material. Erosion works much more slowly than volcanic eruption, yet over long enough periods, it can reshape landscapes and uncover gemstones hidden deep within ancient rock formations. Wind, rain, rivers, glaciers, and changing temperatures gradually wear away mountains and expose stone while carrying sediments downhill toward lower regions. Over millions of years, erosion may expose crystals that originally formed underground. Some gemstones accumulate in riverbeds after erosion releases them from surrounding rock. Because certain gemstones are dense and durable, flowing water may gradually concentrate them in gravel deposits or stream sediments. Humans throughout history often discovered gemstones in rivers and alluvial deposits created through long periods of erosion and transport across the landscape. Gemstone disco depends heavily upon geological timing. A crystal may form underground billions of years ago, remain buried for long periods, then only recently become exposed through uplift and erosion. Human discuften occurs during a small moment within the gemstone's far longer history. The surface landscapes humans see today are always changing over time, even if the movement feels slow compared to human life. Mountains rise and erode, continents shift gradually across the planet, volcanic systems appear and disappear, rivers carve valleys through stone. These changing environments help expose minerals once hidden. Scientists often study gemstone-bearing volcanic rocks carefully because they reveal valuable information about deep environments impossible to observe directly. Kimberlite pipes containing diamonds preserve evidence from the mantle. Ancient volcanic formations record magma chemistry and tectonic activity from long ago. Gemstones therefore become part of a much larger history involving the movement of material through Earth. A gemstone's journey does not end with crystal formation underground. Geological forces must also transport, expose, and preserve the crystals long enough for discoto become possible. Without uplift, eruption, erosion, and crustal movement, many gemstones would remain forever hidden beneath layers of stone underground. Even now, volcanic systems continue operating beneath parts of the Earth, while tectonic forces slowly reshape continents and mountain ranges. Heat rises upward from the mantle, magma moves through fractures. Rivers continue wearing away exposed rock, while buried crystals gradually move closer to the surface through geological change unfolding over time. Tonight, beneath mountains, volcanic fields, forests, deserts, and oceans, forces continue lifting deep materials slowly toward the surface. Eruptions, erosion, uplift, and shifting crust reshape the planet, while gemstones hidden move gradually closer to discovery. Crystals continue their ancient geological journey upward through the restless movement of Earth. Once gemstones reach regions closer to the Earth's surface, an entirely new stage of their geological journey begins. Wind, rain, rivers, changing temperatures, glaciers, and flowing water gradually reshape the landscape while breaking down exposed rock over time. Through these slow surface processes, crystals once locked deep inside mountains or underground formations may become separated from the surrounding stone and carried across the landscape by natural forces. Rivers in particular play an important role in transporting and concentrating gemstones after erosion releases them from ancient rock. Erosion is one of the most powerful shaping forces on the Earth's surface, even though it usually operates slowly compared to volcanic eruptions or earthquakes. Water seeps into cracks inside rock. Freezing temperatures expand fractures. Wind carries abrasive particles across exposed stone. Rivers wear away valleys while glaciers scrape enormous sections of landscape over long geological periods. Bit by bit, solid rock breaks apart and moves through the environment. Humans often imagine mountains as permanent features of the Earth, yet geology reveals that even the tallest mountain ranges are temporary over time. Uplift may raise mountains upward through tectonic pressure, but erosion simultaneously begins wearing them down almost immediately. Over millions of years, entire landscapes can change dramatically, while buried minerals and gemstones gradually become exposed closer to the surface. When erosion breaks down gemstone-bearing rock, the crystals may separate from the surrounding material. Some gemstones are relatively soft and may fracture or weather during transport, while others are extremely durable and resistant to damage. Diamonds, sapphires, rubies, garnets, and additional hard minerals often survive erosion remarkably well compared to the rock around them. Rivers become especially important because flowing water transports broken rock, sediment, and minerals downhill across the landscape. During this movement, lighter materials may continue traveling farther, while denser minerals settle into certain regions along riverbeds, gravel deposits, or bends where water slows slightly. Over long periods, gemstones may accumulate in concentrated deposits created naturally through erosion and river transport. These deposits are often called alluvial deposits, meaning the gemstones were carried and deposited by flowing water rather than remaining inside the original underground rock where they formed. Throughout history, many gemstones have been discovered in river sediments because natural erosion and transport gradually concentrated the heavier minerals in accessible locations. Humans searching for gold in rivers sometimes use similar geological principles because dense materials tend to settle differently compared to lighter sediment. Gemstones behave in comparable ways during river transport. Their density and durability influence where they accumulate after erosion releases them from surrounding rock high in mountains or ancient geological formations. River-transported gemstones may travel far from their original source. A crystal formed underground and later exposed through uplift may break free through erosion, enter a river system, and move many miles across the landscape over time. The gemstone's final resting place may be different from the location where it originally formed millions or billions of years earlier. The movement of water also affects the appearance of transported gemstones. Crystals carried through rivers may become smoother or more rounded as sediment, and flowing water gradually wear against the surface during transport. Other gemstones remain sharper and more angular if they travel shorter distances or resist abrasion more effectively. Landscapes themselves remain in constant motion over time, even when humans perceive them as stable. Rivers slowly shift course, valleys deepen, sediment accumulates in low regions, while mountains gradually erode. Through these processes, gemstones continue moving through the environment long after their original formation underground. Scientists often study river deposits carefully because they reveal information about surrounding geology and erosion patterns. The types of minerals present in river sediment can help identify ancient rock formations upstream or regions where gemstone-bearing material may exist hidden. Surface deposits therefore become clues leading back toward deeper history. Erosion and river transport are patient processes. Human lifetimes are extremely brief compared to the timescales shaping landscapes. A river carving through stone may continue flowing for millions of years while transporting minerals grain by grain toward lower elevations. Gemstones carried within these systems become part of the endless geological recycling of the Earth's surface. Even after gemstones arrive near the surface, their geological story continues. Sediment may bury them again beneath new layers of material. Rivers may transport them farther downstream. Tectonic uplift may later raise ancient river deposits into hills or mountains. Geological processes never truly stop. The Earth remains active continuously across deep time. Gemstones often experience multiple stages of movement and transformation. Formation underground represents only one chapter. Volcanic transport, tectonic uplift, erosion, river movement, and surface deposition all become part of the crystal's long geological journey across the Earth. Tonight, beneath mountain valleys, riverbeds, forests, deserts, and ancient landscapes shaped slowly by water and time, erosion continues breaking down rock while rivers carry minerals across the surface. Dense crystals settle within sediments, while landscapes reshape themselves over time. Gemstones continue their long journey through rivers, erosion, and the endless movement of Earth. The story of gemstones is ultimately the story of Earth. A crystal forms through a long chain of interconnected geology, linking the deep interior of the planet with mountains, rivers, volcanoes, oceans, and surface landscapes always changing over time. Heat rising from the mantle influences magma formation. Tectonic forces reshape continents and bury rock underground. Fluids carry dissolved minerals through fractures underground. Erosion later exposes crystals at the surface, while rivers transport them across the landscape. Humans often separate the planet into categories such as mountains, volcanoes, rivers, oceans, and underground rock. Yet geology reveals that these environments constantly influence one another. Deep mantle heat drives tectonic movement. Tectonic movement shapes mountain ranges and volcanic systems. Mountains influence erosion and river flow. Rivers transport minerals toward oceans and sedimentary basins. Beneath the surface, all these systems remain connected through the movement of heat, rock, water, and time. Gemstones preserve evidence of this interconnected history inside their crystal structures. A diamond may record pressure conditions from deep within the mantle. An emerald may preserve evidence of mineral-rich fluids moving through underground fractures. A ruby may reflect metamorphic transformation beneath ancient mountain ranges. Gemstone becomes a physical record of environments that existed long before humans appeared on Earth. Much of the planet's activity unfolds too slowly for direct human observation. Mountains rise only tiny amounts within a human lifetime. Continents drift gradually across the surface over millions of years. Crystals grow atom by atom underground, while erosion slowly reshapes valleys and river systems. Yet over time, these slow processes transform the appearance of the Earth. Time itself becomes one of the most important ingredients in gemstone formation. Heat and pressure may create the right conditions, but without long periods of stability, crystals often cannot grow into large organized structures. Volcanic systems may transport deep materials upward, yet erosion still requires immense time to expose buried minerals at the surface. Geological change depends heavily upon patience operating across deep time. Humans sometimes struggle to imagine deep timescales because life unfolds so quickly by comparison. Entire civilizations may rise and disappear, while a mountain range continues slowly forming through tectonic collision. A gemstone resting in sunlight today may have begun forming before dinosaurs existed, or before continents separated into their present positions. Geological history stretches across timescales far larger than human memory or written records. The Earth remains dynamic because energy continues flowing outward from deep inside Earth. Heat drives mantle movement underground, while tectonic plates slowly shift across the surface. Volcanoes erupt. Oceans open and close over time. Mountains rise while erosion gradually wears them down again. These interconnected systems constantly recycle rock, minerals, water, and heat through the planet. Surface processes and deep earth processes influence one another continuously. Volcanic eruptions bring deep material upward, while erosion removes surface rock and changes pressure conditions on buried formations below. Rivers transport sediment across continents, while tectonic uplift reshapes drainage systems over millions of years. Even climate influences erosion rates and landscape evolution across deep time. Scientists often describe the Earth as a dynamic system because nothing remains permanently fixed. Continents move, crust forms and recycles, minerals crystallize and transform under changing conditions. Gemstones themselves may weather, fracture, or become buried again within future geological cycles. The planet remains active continuously, despite appearing stable during the brief span of a human life. Gemstones can survive many stages of Earth history while preserving evidence of changing environments. A crystal may form underground, rise toward the surface through tectonic movement, survive erosion and river transport, become buried again within sediment, and later reappear after additional geological change. The gemstone becomes part of the ongoing transformation of the planet itself. The hidden processes shaping gemstones continue operating underground tonight. Mantle heat moves slowly upward through the crust. Mineral-rich fluids circulate through fractures underground. Mountains continue rising and eroding. Rivers carry sediment toward distant oceans. Underground, crystals continue forming, while older gemstones move gradually through new geological cycles. Gemstones reveal how natural beauty can emerge from patience and powerful forces working together over time. Pressure, heat, chemistry, water, erosion, and tectonic movement all contribute to crystal formation. What humans admire as a polished gemstone represents the outcome of countless interconnected geological events unfolding for billions of years. Tonight, beneath mountains, oceans, volcanic regions, forests, deserts, and river valleys spread across the surface, geological systems continue interacting through heat, pressure, water, movement, and time. Underground, crystals continue recording the history of the planet within their structures, while Earth remains restless and dynamic beneath the calm darkness of the night. Underground, hidden far below mountains, forests, deserts, oceans, and cities, gemstones continue forming tonight through geology older than human civilization itself. Heat rises slowly from the planet's interior, while pressure compresses buried rock underground. Mineral-rich fluids move through fractures underground. Magma cools inside hidden chambers, while atoms organize themselves into repeating crystal structures over time. What becomes a polished gemstone resting in human hands often begins as part of a vast geological story unfolding for billions of years within the restless interior of the Earth. The journey of gemstone formation begins with the fundamental ingredients of geology itself. Chemical elements combine into compounds, while atoms arrange themselves into organized structures by the laws of chemistry and physics. Heat influences atomic movement underground, while pressure shapes mineral stability and crystal structure. Under the correct conditions, crystals begin growing slowly within magma chambers, metamorphic rock, underground cavities, or mineral-rich fluid systems hidden. Some gemstones form from slowly cooling magma, where minerals crystallize gradually as temperatures decrease underground. Others develop through metamorphism, as existing rock transforms under intense heat and pressure during tectonic collision and mountain building. Additional gemstones grow from heated fluids, carrying dissolved elements through fractures and cavities, where changing conditions allow crystals to form layer by layer over time. Gemstones depend upon patience and stability. Crystal growth usually happens extremely slowly. Atoms attach themselves one by one to existing crystal surfaces, while organized patterns continue extending outward through time. In rare environments where conditions remain stable for thousands, millions, or even billions of years, crystals may grow into forms hidden. The Earth itself remains dynamic throughout this process. Continents drift gradually across the surface. Mountains rise and erode. Mantle heat drives tectonic movement underground, while volcanic systems transport deep materials upward toward the surface. Rivers reshape landscapes, while erosion slowly exposes crystals once buried beneath miles of rock. Gemstone becomes part of this immense interconnected geological system operating continuously across deep time. Diamonds preserve evidence of the deep mantle where carbon bonds under pressure underground. Rubies and sapphires reflect metamorphic environments shaped by tectonic forces and underground heat. Emeralds reveal the movement of mineral-rich fluids through fractures underground. Quartz geodes preserve hidden crystal growth inside underground cavities, where space and stability allowed symmetrical structures to expand gradually over time. Color itself becomes part of the geological story preserved inside gemstones. Tiny trace elements incorporated into the crystal during formation influence how light interacts with the mineral structure. Chromium may create red ruby. Iron and titanium may produce blue sapphire. Copper, manganese, vanadium, and additional elements contribute to the diversity of colors found throughout the natural world of gemstones. Light later reveals what geology prepared in darkness underground. When sunlight enters a crystal, internal structure and chemistry shape the movement of different wavelengths through the gemstone. Transparency, brilliance, reflection, and color all emerge from interactions between light and atomic organization established underground long before the crystal ever reached the surface. The journey from underground formation to human discovery requires enormous geological change. Volcanic eruptions transport mantle material upward. Tectonic uplift raises buried rock toward the surface. Erosion removes overlying layers, while rivers carry dense minerals across landscapes over time. Without these additional processes, most gemstones would remain permanently hidden. Gemstones preserve hidden records of Earth history inside their structures. Crystal growth patterns, inclusions, trace chemistry, and mineral composition all contain clues about the environments where formation occurred. Scientists study gemstones not only for beauty, but also because they reveal valuable information about deep Earth conditions impossible to observe directly. Humans have admired gemstones for thousands of years, often associating them with wealth, mystery, protection, spirituality, or beauty. Ancient civilizations valued crystals long before understanding geology or atomic structure. Yet even today, modern science continues uncovering new information about the processes shaping gemstones underground over time. The Earth remains active tonight just as it has throughout history. Deep mantle heat continues moving upward underground. Mineral-rich fluids circulate through fractures hidden. Mountains continue rising, while rivers slowly reshape the surface of continents. Crystals continue growing atom by atom within cavities, magma chambers, and metamorphic rock beneath landscapes sleeping above. Gemstones reveal how beauty can emerge from pressure, heat, time, and transformation, working together for billions of years. What appears small enough to rest within a human hand may contain the history of continents, volcanoes, mountain ranges, deep mantle processes, underground fluids, and ancient geological change preserved within a single crystal structure. Tonight, beneath mountains, forests, oceans, volcanic regions, deserts, valleys, and ancient stones spread across the Earth, gemstones continue forming in darkness underground. Heat, pressure, chemistry, water, and time continue shaping crystals underground, while the restless planet slowly changes above them through endless geological movement across deep time itself. Thank you for listening to the Sleepy Mind channel. I hope you enjoyed learning about how gemstones form underground and the forces that shape crystals underground of our planet. Good night.